Welcome back to the Engineering Why. Look, if you've been anywhere near systems engineering lately, you've absolutely heard the dominant narrative, right? C++ is legacy, it's inherently dangerous, and we need to retire it immediately. But as veteran engineers, we know there's a massive difference between a high-level narrative and the physical, bare-metal reality of our hardware. Okay, let's dive into this. Today we're doing a full explainer that looks right past the headlines. We're going to examine the true cost of memory safety, not as some theoretical Twitter debate, but as a hard, physical engineering trade-off.
Here's our roadmap for this explainer. We're starting at the top with the government security mandates, and we'll drill all the way down to bare metal cache lines. So we've got 1. The 2026 security mandate. 2. The memory safety tax. 3. Microseconds in markets. 4. The deterministic frame budget. 5. Cache hierarchy and hardware. And wrapping up with 6. Specialization, not replacement. Let's get to it.
Section 1. The 2026 Security Mandate. Rethinking critical infrastructure. All right, so we have to start by acknowledging the undeniable massive shift pushed by international cybersecurity authorities over the last couple of years. The safety argument is totally serious, and it's grounded in real data. Just look at this timeline. Back in the 1970s, C and then C++ gave us the era of manual memory control. Incredibly powerful, but yeah, inherently sharp. By 2015, we saw the rise of modern memory-safe alternatives that could handle systems-level tasks without those same risks. And that brings us to January 2026, when CISA and the NSA drew a line in the sand. They issued a joint mandate for software manufacturers to transition to memory-safe languages for critical infrastructure. You know, past security shifts have definitely influenced industry standards, but this is the most direct intervention we've ever seen.
And honestly, they have a totally valid point. The NSA found that between 66 and 75%, let's just call it 70% on average, of modern exploitable vulnerabilities trace directly back to memory safety failures. These are the exact kinds of failures C++ is structurally prone to. If you're building critical infrastructure, we're talking power grids, water systems, public-facing government services, the government's argument for safety is absolutely bulletproof.
Moving to Section 2, the memory safety tax. What runtime safety actually costs.
But here's the thing. Software engineering isn't a one-size-fits-all discipline. Safety mechanisms at the application layer aren't just magic. They are actual physical additional operations. And in computing, additional operations require time. First, let's define what we're actually preventing here. A memory safety violation happens when a developer mismanages memory. Think buffer overflows or those nasty use-after-free bugs. Memory-safe languages fix this by simply taking that management decision away from the developer. The language enforces rules that make these mistakes structurally impossible. Now, removing our ability to make these errors is absolutely incredible for security, but it requires compute. Safety is not a free lunch.
Now, what's really interesting about this slide is how we can visualize that cost. Think of C++ as a warehouse where workers pick up and put down boxes completely freely. They trust their own judgment. It is maximally efficient, but yeah, highly prone to human error. Runtime safety, on the other hand, is like adding a warehouse supervisor. Every single time a worker wants to handle a box, they must check it out with the supervisor who tracks its exact location. Is it infinitely safer? Absolutely, but it adds overhead to every single transaction.
Section 3. Microseconds and markets. Let's look at high-frequency trading. This is where we have to face the physical reality of domains that simply cannot afford to wait in line for that warehouse supervisor. And this brilliantly illustrates exactly what I mean. The Bloomberg 2026 Performance Benchmark Report quantified this execution timing gap. In latency-critical applications, C++ serves as our base 0%. Rust, which is the most efficient memory-safe option out there because it enforces safety at compile time, still runs 15 to 20% slower in these specific extreme latency scenarios. And languages reliant on garbage collection? Forget about it. The latency gap is massive. When you're competing for a trade, a 15% delay isn't just a slight disadvantage, it's a total failure.
And this right here is exactly why you see these crazy salaries of $200,000 to $500,000 for expert C++ engineers at firms like Citadel, 2 Sigma, and Jump Trading. In high-frequency trading, timing is completely binary. If your order arrives at the exchange even 1 microsecond later than your competitor, you get absolutely nothing. The enormous economic weight of microsecond optimization dictates their tooling. They achieve safety through rigorous static analysis and incredible engineering discipline, precisely because language-level safety mechanisms are fundamentally incompatible with their strict timing constraints.
Let's move to and see how this builds into Section 4, the deterministic frame budget in AAA game engines.
Let's step away from the financial markets for a second and look at the strict mathematical limits of AAA game engines. To really understand the game engine constraint, you have to understand the stop-the-world pause. This is an automatic, totally unpredictable interruption where a garbage collector just halts all program execution to clean up unused memory. Now, if you're building a cloud microservice or a web app, an occasional pause of a few milliseconds, completely invisible, nobody cares. But for systems requiring absolute timing predictability, a stop-the-world pause is catastrophic.
So the crucial point is this math right here. To hit a smooth 60 frames per second, a game engine has a strict, unyielding 16 millisecond deterministic frame budget. Check out this breakdown. You've got 3 milliseconds for physics, 4 for animation, 7 for rendering, and 2 for audio and input. Boom, that is your 16 milliseconds. If a garbage collector decides to unpredictably pause the system for 4 milliseconds to clean up memory, guess what? You miss the frame. The player feels a visual stutter. It totally ruins the experience. C++, however, allows engineers to pre-allocate memory at level load time and ensure zero hidden runtime debt during active gameplay.
Section 5. Cache hierarchy and hardware. The true physics of memory. All right, we need to drill down to the bare metal here. If you want to mentor junior developers and turn them into senior systems engineers, you have to teach them the physics of modern CPUs. The physical reality is that modern processors operate way faster than main memory. So, to compensate, they use a hierarchy of caches. When the data your CPU needs is sitting right there in the cache, what we call a cache hit, it is blazing fast. But when it isn't a cache miss, the CPU literally stalls and just waits for main memory to catch up. To avoid these stalls in real-time systems, performance absolutely requires localized memory access patterns. You literally have to group related data together physically. This is called data-oriented design, and to pull it off, you need total manual memory control.
And this is the true superpower of C++ in 2026. It gives you the absolute control over deterministic memory layout that veterans need to squeeze every single nanosecond out of the hardware. You can align memory precisely to cache line boundaries. Automated garbage collectors, by their very nature, decide where objects live based on their own internal management strategies. You can't just override it. When you need to bypass unpredictable layouts to prevent cache misses, manual memory management isn't just some legacy feature, it's a strict physical requirement.
Finally, Section 6. Specialization, not replacement. Let's zoom back out to the high-level industry view for a minute and dismantle this binary C++ is dead narrative. Because honestly, it's an intellectually lazy frame, and we need a much more pragmatic, balanced synthesis. C++ is not static. C++ 26 has introduced hardened features that don't sacrifice manual control, but have actually been shown to reduce production seg faults by 30%. The language is actively evolving to address safety. At the same time, Rust has rightfully been adopted by 60% of enterprises for new projects, and that is fantastic. But the real goal here, it's appropriate specialization, not universal replacement. Both these tools are just maturing into their correct roles.
We really must clearly delineate the domains. If you're building operating systems, cloud infrastructure, or critical security services, where a single memory bug literally means a national security breach, you absolutely should be using memory-safe languages like Rust or Go. It's a no-brainer. But if you are building high-frequency trading algorithms, AAA game engines, or hardware-level embedded control systems, C++ remains precisely the right tool for the hard, physical constraints of your industry.
Ultimately, it's all about using the right tool for the physics of the problem you are solving. So I want to turn this over to the senior engineers watching this explainer right now. How do you balance the real cost of memory safety against strict latency and deterministic budgets in your own real-world systems? Are you guys utilizing C++ 26's hardened features, or are you adopting Rust for specific microservices? Drop your engineering experiences in the comments below. I'd love to read through how your teams are handling this on the floor. Thanks for joining me on this deep dive, and I'll catch you in the next one.